So let's consider more examples. So far we have applied the probabilistic method to solve some problems in combinatorics related to graphs and hypergraphs. And also, probabilistic method applies to some number theoretic problem. Let's consider one example. We say a subset A of an abelian group G is sum free if A plus A is a set of all numbers element of the group G, which is obtained by summation of two elements in A. Does not. So if this does not intersect with A, then we say this is sum free. In other words, there are no triple A1, A2, A3 in G with A1 plus A2 plus equal A2 equal A3. So it has no solution of this equation where the X and Y, G all consist of the elements from A. So for example, if you consider all odd number in a natural number set, then this is sum free because when we add two odd numbers, it's always even, which is not in A. So one of the typical, one of the questions is that when an abelian group is given, how large a sum-free subset could be. More generally, when an abelian group is given, and we have some set, arbitrary set B, can you find the large sum-free subset A or B? So one of the results that we will show is that if you have a set of integer, say non-zero integer, because if we have a 0, then 0 plus 0 is 0. So this again is a solution of this equation. So it cannot be a sum-free set if it contains 0. So if we have a non-zero element, n non-zero integers, then it always contains a sum-free subset A with size bigger than 1/3 n. So no matter what integer set is given, we can always find the subset which has size roughly 1/3. We can delete 2 out of 3 so that the remaining one is sum free. So how do we want to prove this? In order to prove this, we have the following observation. So one of them is that when P is large, GP and G are almost same. That's not a good way to say. So this is finite set. So if we take P be larger than say Bn, then this being sum free set and this being sum free set in this integer group is almost same as this being sum free set in this GP. So each number is also an element in this GP. And if P is large enough, let's say it's much larger than Bn, then this sum is also in GP. So this being, some free in here and some free in here are similar. And then in GP, it's actually number which is wrap around. Here, if we take a 1/3 set of size p over 3 and 2p over 3, then this middle part forms a sum free set. So if you add a 2 number here, then it's always as big as here. This is bigger than 2p over 3 and smaller than 4p over 3, so it doesn't wrap around and come here. So that's one observation. And another observation is that if A1, A2, A3, A1 plus A2 equal A3, then XA1 plus XA2 equal XA3 is also same. So meaning that A is sum free, then XA, which is X times A, where A is in A, is also sum free. This sum free, let's say X is not 0, and this sum free. So with these two observations, how we will prove it is that when you have this set B, and from here we will consider a corresponding set in some GP. And then we will multiply it with random integer x. And then when this is random, then these are scattered around, and then we will show that many points lie in this middle piece. So that we can find, in XP, we can find a large set which lies in here and sum free. And then we transfer this subset back to B, then that's also sum free set. So that's roughly what our plan is. So let's make it rigorous. So let's say P is 3k plus 2, be a prime number, such that P is bigger than the absolute value of Bi for any I. And let C be the subset of this cyclic group, where this consists of k plus 1 up until to 2k plus 1. Then note that C is a sum free set of this cyclic group GP. And as I mentioned before, now we want to correspond this B into here in a random way by multiplying some number x. So we choose an integer x between 1 and p minus 1 uniformly at random. And let di be the element in GP which is same as x times bi. Of course, we have to take the modulo p because we are considering this in a cyclic group GP. Then, as x ranges over all numbers between 1 and p minus 1, the number di, so bi is non-zero number, and then you multiply 1 to p minus 1, and p is a prime number. So this also ranges over all non-zero element of GP because P is prime. Then what's the probability that this DI is in C? then each element of C is being picked with probability 1 over p minus 1, because this could be each of these with the probability 1 over p, which is k plus 1 over 3k plus 1, which is bigger than 1/3. Hence, if x is randomly chosen, then if we consider the numbers d1 to dn, which only lies in C, this has expected size larger than n over 3. So what's the expectation? Expectation is like average. So if you know the expectation, you know that there has to be an event where your value is as large as the expectation. So expectation is like average. So if you have several numbers, and if you know the average, then there must be at least one element which is as large as the average. And similarly, you have many events, and then you know the expectation, then there has to be at least one event which performs as good as the expectation. So there exists x in here and a subset A of B of size bigger than n over 3, such that xa modulo P is in C for all A in this A. So that means, so C is sum free. xa1 plus xa2 is never xa3. So this happens for all a1, a2, a3 in A. That means a1 plus a2 is never a3 in A as well. So only, let's say, this direction is true, because if a1, a2, a3 satisfy this, then we know that xa1, xa2 equal xa3 in mode P, which is contradiction that a1, a2, a3 are all in C. So this says A is sum free. So we have a set A which is sum free, and A is a subset of B with a size bigger than n over 3. So this proves the theorem. So here we consider this integer set, which is one abelian group, and then we consider the subset. Then we can ask the similar question for more general abelian group. So Alon and Kleitman show that for general set B, which is subset of arbitrary abelian group, and it has n elements, then this B contains a sum-free subset A with more than 2n over 7 elements. And this 2n over 7, so this 2 over 7 is best possible by considering this specific abelian group. And also, what's for this integer case? This integer case, this 1 over 3 is best possible, because Eberhard Green and Manners in 2013 proved that this cannot be improved to 1/3 plus epsilon for any epsilon positive. So you cannot expect this much. But obviously, of course, I mean, this does not actually forbid any improvement of like 10 or 100 or square root of n, which is smaller than epsilon n for large n. So we don't actually know what's the correct function here should be. So here, one of the technique we used is that when we have a certain, object which is chosen at random, and then we know the expectation. Then once expectation is known, then we can conclude that there is at least one choice, choice that we made at random, which is this x. There is at least one choice which does as good as the expectation. So that's one technique that we will learn more later. And in